Okay, so we've got our video here. This will be on interaction of light and matter, and then moving into interference patterns and single slit diffraction. Just so you know, I am in a public place, so I apologize if the noise comes through a little too much, but I should be talking loud enough that you hear me clearly. All right, so the first thing that we'll go over is just these four words that are on the screen. Right, light is this electromagnetic wave, so um, we've got just our interaction here, right? Our E field um, over position or over time, whatever you want to look at does that. Right, our B field is going to come right out of the page, then away from us, out of the page, into the page, out of the page, all that kind of good stuff. But the E field is what we're really looking at there. So that electric field oscillating as a function of time. Okay, but electric field, right? Electric fields interact with charges. So matter is made up of charges. That means things will interact with electromagnetic waves. So you've got a few things that can happen when an electromagnetic field hits a wave. Emission. This is when something emits its own electromagnetic waves, like a stove. So that's what this one right here is for. So when it looks hot, it's just because it starts as emitting infrared rays. That's what we feel as the heat. But if it gets warm enough, then it'll actually emit visible light, and that's what we see as this orange, the orange glow. Absorption. Absorb. When anything is absorbed, that means we will not see light coming from it. So when we don't see light, that's what we see as the color black. Oil is a very good, like petroleum products is a really good example of that. They absorb almost every single part of the visible spectrum. That's why they are so dark black. When things transmit, that's when light just moves through. Um, and then reflection is when we see something that we are not looking at ourselves, but is reflected off of a surface. You use those probably every day with a mirror in the morning. All right, so there's the four things that can happen when electromagnetic waves interact with matter. We can see here, right? This is a reflection. This is almost a perfect reflection of beautiful. I think this is Mount Rainier, but just gorgeous picture there. That's called specular reflection. When our incident rays are parallel to each other, right? Incident. This is what we call incident when they're coming in, and then reflected over here when they're moving out. So incident rays are all parallel to each other. The reflected rays are all parallel to each other. That's why we get this really clear picture. This is something called a virtual image. We will go over more of what that means later when we look more at images and lenses from mirrors and lenses on all that. But incident reflected rays, it's called specular reflection when we get a really clear picture. As opposed to, right, this is what we see more often from water when we get this kind of this messy picture here, especially that duck, that darn duck in the middle, kind of messing up everything that we have there. This is called a diffuse reflection. Right, we've got example of light reflecting off paper. Right, we see the paper, which means light reflects off it. Now, it's not going to be a normal thing that we think about as a reflection, but light reflects off paper. This is how we see things when it's reflected. So, just the fact that you are looking at anything that's not producing its own light, that is a reflection. It's just a diffuse reflection if you don't see an image of something in that reflection. What happens here is the incident rays come in parallel, right? The incident rays are coming in from whatever the light source is, probably the sun, or the light bulb above you, whatever it is. But the reflected rays are not. The reflected rays are kind of just all over the place. They make all these weird little angles when they are not when they're not parallel with each other. That means we will still get light into our eyes so we can see the object. However, we will not get a clear picture or a clear image. So that's why everything that you see around you that doesn't produce its own light, it does make its own reflection. But we don't think about that normally as a reflection because we can't see an image behind it. Okay. All right, just more examples of all these. Just take a moment, pause the video right now. What do you think each of these four shows us? What do you think each of these four shows us? Pause the video right now. Go. Okay, so this is transmission or absorption. Transmission, absorption, because this is an X-ray. This is an X-ray of someone's hands, right? The white parts where the bones are, that's where the X-rays are getting absorbed, so we don't see it. Whereas the darker spaces, right over here, and then we get about, sorry, I'll get ahead of myself. The darker spaces, anywhere there's not white, that is where the X-rays are being transmitted. So we can see these really clear pictures because we get this whole gradient, right? Your skin will transmit most of them, but you can still see that there's skin or that there's soft tissue there. It's really cool that you can see, if you look at this, like right here, you can see the wrinkles in someone's palm, because the wrinkles will absorb or transmit different amounts of them. Okay, this one over here, we're looking primarily at this rainbow here, and this rainbow is showing us transmission. Um, More specifically, it's showing us a type of transmission called refraction. And we'll talk about this more in detail. We'll learn how to do more math with that in future classes. But that's a type of transmission. It is called refraction, right? Because the sun comes from the sun, again, to somewhere below about 35 degrees above the horizon, comes down, hits the little droplets of water in that rainbow, and then comes right at us. And it depends what the wavelength of light is. That's why we can separate it out into all the different colors, because the angle that it refracts at, is going to depend on the wavelength of light or the color. All right, moving down here, this is an example, right? Either not transmission, whoops, reflection, or reflection, if I can write, or absorption, right? Reflection or absorption. Right, the reflected part, that's going to be the white stuff. Anything that's white is reflected. It's just a diffuse reflection. So we get a diffused reflection because we see the paper. Diffuse reflection is we see the paper, but we don't see an image behind it. Whereas the black ink, all this black ink here that makes up the letters, all the letters down here, all that black ink is absorption. I think that's a French newspaper. I have no idea what any of it means, but there we are. Reflection and absorption. And then this fire, this last one down here, maybe you have this by now, but this one is emission, right? It is producing its own light. What actually happens there is we get the nucleus, and then we have the electron rings around the nucleus. And if we have, let's say there's a little electron on this first one, what happens is the infrared, that's the heat from the fire, the infrared gets absorbed. I should start with this electron, one energy level higher. The infrared gets absorbed, so that's infrared radiation or IR. The electron gets excited and jumps up. The electron jumps up an energy level. Then when it falls back down, if it happens to fall back down with some amount of energy that turns into visible light, that's when we see the flames. That's when we see all these flames. So typically for just air molecules, which is primarily nitrogen, right? Nitrogen produces that yellow or orange that we see as fire. But if you burn other chemicals, you get different energy jumps. It produces different colors. That's something that we'll talk more about in, guess what? Unit 7. Okay. Transmission and absorption. There's a few different types that things can be. Transparent is transmitting without distorting. So transparent, that's like a window. That's the goal of a window, is to transmit without making anything distorted. Translucent, on the other hand, that might be like a fogged shower, or one of those. I mean, you see these mirrors, like the foggy mirrors, windows. These windows that are hard to see through, that it kind of distorts the picture. You can see a little bit, but it's a little distorted. as opposed to opaque, right? That's like a door, or actually a mirror. A mirror is considered opaque because you cannot see through it. Mirrors are considered opaque. So absorbing or reflecting everything that is opaque. Um, the fact that you are looking at your computer and not through your computer or phone or whatever you're watching this video on, that means that that is an opaque surface. When you're seeing light, so your computer or your screen is emitting light, so your screen's acting as an emitter or has that emission, but it is all absorbed or reflected, everything that you get there, because you can't see through your computer. Just a little bit on reflection. We won't do much math with this right now. We'll get more into the math of reflection and refraction later. But reflection um, reflection is defined as the incident angle. Right, so we have our incident ray coming in from over here. The incident angle to the normal line. Right, the normal line just means it is perpendicular to the mirror or whatever you're reflecting on. But we know that the incident ray equals, or the incident angle equals the reflected angle, and that's just a property of all this light. Refraction, right? This is a great example of refraction. Is the pencil, you would think, is just going to continue. If I can get a straight, oh, I've got a ruler here. Nice. Um, if we just take this straight line along the ruler, this is what we get for our pencil line. But right where it hits the water, you can see the pencil is kind of over on the left side of it. But then where it's down at the bottom, the pencil's over on the right side of it. That has to do with the curvature of the glass, right? Because the glass is curved one way at the bottom on the left, and it's curved the other way at the bottom on the right. So that's why it switches over that straight line. We will do more math with this later, but just to introduce you to this idea of refraction, that's what refraction is. You can kind of think about refraction as, right, if you have a car that's just on the road, that car's just going to drive normally. But if you have a car that's half on, half off, right, when your tires hit the grass, they can't move as quickly through the grass. But when the other side of the tires, those are on the road, these tires are on the road, they can move at their normal speed. So what's going to happen to this if the right side of the car can't keep up with the left side of the car is going to turn and go off that way because the right side slows it down, but the left side keeps going just the same. So that's what we see in light when we get refraction. When we get this picture right here, this is a picture of going from air into water. When we have something going from air into water, because if you get say we get a little particle right here, this particle is going to be moving forward until it hits this thing that makes it slower. But what about this other particle that's on its right side? It'll move through it the same way, but the particle on the right side, or I shouldn't say particle, the photon, these photons on the right side, this hits the slower one first. So when you hit the one that you can't move as quickly through, this will slow down, but the other one keeps going. This is just like the left side of the car and the right side of the car. And that's why the car turns to be going that way now. You can look at that for any 2 points on any of these little wave lines. These kind of just represent the wave fronts, which just means a normal or a regular portion of a wave, but across everything that's being emitted right next to it. Because these waves, wave fronts are kind of like ocean waves. You get one wave that all just travels. Oh, sorry. You get one wave that all travels just parallel with each other. It's parallel to the wave behind it, all those kinds of things. We can think about electromagnetic waves in the exact same way. So that's just an intro to refraction. We won't do anything mathematically with that yet. But to kind of move on from that, the next thing that we're going to talk about, and this is something we've already talked about a little bit, is interference patterns. Interference patterns. If I get a wave that does this, if I get a wave that does this, right, that's our electric field. And then if we take our magnetic field might be doing this. Okay, so we've got our B field vectors here. Right, the B field is coming out of the page at us. And then over here, B field's going away from us and then out of the page at us. Whereas our electric field, we're just going to say is going up and down, up and down. So that's our electric field, right? Our electric field. And this one over here is our magnetic field. And you can use your right hand rule, right? Pointer finger with E field, middle finger with B field. That tells us that the velocity of our wave is to the right. Let's call that the x-axis, the y-axis, and the z-axis. Okay. So, as this electric wave goes through, what happens? What happens if, let's say I put this wave in a tube. Well, we're going to have this wave that does this, but then when it hits the side over there, I'm going to redo that wave. Wave in a tube, when it hits the side right there, we've kind of already looked at this, but how do transverse waves reflect off the end of a surface? Well, a transverse wave will reflect, and I'll just use green for the reflection, by going down at that, right? This wave has kind of this negative y-axis component, so it'll continue that when it reflects off. So it'll do this reflection piece, and I'm sorry I didn't draw this wave perfectly, but you know my drawing skills. This wave reflects, and then it has the same exact wavelength on the way back. Well, if you remember, let's make this a little bit thinner. I'm going to try to draw a straight line here. The ruler is really coming in handy today. Well, I should say it would come in handy if my initial line was straight, which it wasn't quite. Okay, pretend that this is all straight and passes through the middle at every single one of those wave intersections. Okay, so we get these places here where they all go right through that axis, right there. Right, we kind of talked about this before, but these are called, I don't know what just happened there. Those are called nodes. These are called nodes. So all these nodes here, are places where, right, the electric field, both on the way there and the way down, so on the way to the end, but then on the way back from the end, these nodes are places where the electric field is 0. So E field of 0, right, an electric field, volts per meter, and on the way back, 0 volts per meter. Well, what happens when you add up 0 and 0? You get 0. So this spot here, every single one of these, and these are nodes, every single one of those nodes is going to have 0 electric field always, forever. As opposed to, let's take a look at, right, if we keep going doing all this, if we take a look at one of these spots, and as this wave reflects, one of these spots that has the maximum amplitude from both ways, we get either, and it just depends on where the wave's at in its oscillation, we get either all the way up to its amplitude or all the way down to its amplitude. All the way. So we get either a positive amplitude, try to do this in green. We get either a positive amplitude or we get a negative amplitude. And what actually happens, right, is all these waves are oscillating all the time. So what happens is this actually, we get +2 because the red and the green combine. So the red wave and the green wave combine because they oscillate up and down, and when they happen to be in phase, they will oscillate all the way up together or all the way down together. So we get these waves that are twice as tall. They have twice the amplitude, but then they have these little nodes that just live in between. So what ends up happening is instead of the wave looking like that, we get a wave that looks like just one standing wave that goes from goes from what it was before to now it's twice the amplitude. Twice the amplitude there. And if this is just a look at one instant in time, the red and the green are just different instants in time. And the green is just a different instant in time where it happens to be going the other way, but it's twice the amplitude. This is a phenomenon we call a standing wave. Standing wave. And this has to do with interference, constructive and destructive interference. So places where we have double the amplitude, that is constructive interference. At places where we have uh, constructive interference, at places where we have a node, so antinode is what this is called, antinode. At places where we have a node, that is called destructive interference. Destructive interference. Uh, so as we have this constructive and destructive interference, this creates a standing wave because it looks like the nodes are just in place always. Okay, and I know we've kind of looked at this with the ropes before, but that's a standing wave. So we get constructive and destructive interference. Just remember this is because at this point we have some E field vector. I'll do this from red. We have some E field vector up from red and some E field vector from the reflection. Both of those have an amplitude of A, so we end up getting this amplitude of 2A. As opposed to down here, when they're both pointing the same way down, A, we get an amplitude of 2A. But then the node, right, we're going to have, I'll do this in red and green again, sorry. We have this is amplitude of A, whereas the red might have an amplitude of negative A. So that ends up giving us this spot where those electric field vectors just cancel out. They just cancel out, and that's what a node is called. Okay. We are going to do and by the time you watch this video, maybe we've already done this, but a demonstration in class with 2 speakers and just listening at different places around the room to talk about this constructive versus destructive interference. Maybe we can get the ruler to go away. Okay. This constructive and destructive interference. Because what happens is if we get a speaker, all right, let's say we get a speaker and a speaker. This speaker emits sound waves that kind of oscillate out, and I'm just going to call these wave fronts. These are just the wave fronts. I'm going to try to make them as evenly spaced as I can, but I'm terrible at this. All right, so that speaker creates those sound waves. And this speaker creates sound waves exactly the same way. And I'm going to try to make these, once again, try my very best. Oh, cancel. Try my very best to make these, oh, that was a bad one, evenly spaced. What we get, so these wave fronts, by the way, this wave front is going to be anywhere, right? That's our wave. The wave fronts are going to be like right here and right here. I'm just going to call those the tops of the waves, just like an ocean wave. The wave front, well, if we have a place right here, let's just take a look at right here where we have the wave coming from the right speaker and the wave coming from the left speaker. That's going to have the amplitude from the right speaker and the amplitude from the left speaker. So overall, this will give us a spot of double the amplitude. That is constructive interference. That is constructive interference. As opposed to, right, if all these lines represent the top of the wave, then we get these places that are right at the bottom of the wave. So the bottom of the wave, I'm sorry. We get places like this where we have, I'll do it over here. We have, let's say, the top of the wave from the left speaker, but then we're right in between the wave fronts for the right speaker. So we're at the bottom of the wave. It's right from, I'll just label this left speaker and why not brown right speaker. So the left speaker, we have an amplitude of A. But from the right speaker, we have an amplitude of negative A. So what's our overall amplitude going to be right there? Yeah, our overall is going to be 0. So that is called destructive interference. Destructive interference. I'm going to erase that momentarily, or erase that right now, just to show you something else a little bit more cool. Right, so all the intersections where we have an intersection of everything all at the same place, that's our constructive interference. If we take a look at our constructive interference, we can kind of see that there are patterns of straight lines, and if I was better at drawing these wavefronts, they would be a lot straighter. But these patterns of intersections right here, and these lines I'm drawing here represent places that are really loud. Right? These will have double the amplitude, as opposed to right here, right, where we pass through these areas of destructive interference where one's at its amplitude maximum, the other's at its amplitude minimum, so those cancel out. These lines here represent minimums. These lines represent the minimums where there's 0, or at least very low amplitude. So right, the reds are constructive interference, where we have either both waves are at their peaks, right? Both waves are at their peaks, or right in the middle, both waves are at their troughs, which will just give us an amplitude of negative 2A as opposed to positive 2A, negative 2A, positive 2A, all that. So we'll get this really big wave along this red line, as opposed to over here, we've got 1 at positive A, and we've got 1 at negative A, so that's a 0. This one, that's a 0, 0, 0, 0, 0, because one's positive, one's negative along the whole orange line. And you can see these orange lines emanate out like that, and they go kind of in straight lines. So let's say you were a person. Well, okay, I don't have to say you're a person. Let's say there is a person. Oh, that's a bad smile. That's okay. Let's say the person walks along the room, just walks along the other side of the room here. Well, you're going to hit this place of constructive interference where the music's really loud. And then you'll hit, all right, where we get all this, then you'll hit this place of destructive interference where the music's really soft. You get a place that's really loud, a place that's really soft, a place that's really loud, a place that's really soft. Again, loud, soft, soft, loud, soft, all that. So you're just going to hit these places where on the other side of the room you'll just walk around and you'll hear all these different volumes from loud to soft, from loud to soft. So as you're walking, you will actually get this wave that from loud to 0, from loud to 0, loud to 0, loud 0, loud 0, loud 0. And that'll just go all the way along. So that's going to be, you're going to do volume, and I mean sound volume, and just as your position changes, it's just as you walk along the side of the room, you'll go from either really loud or really soft. This is just one of our really cool phenomenon of constructive versus destructive interference. So this is for two sources of waves, right? One source of waves, two sources of waves. Two sources of waves that are in phase. That means that they're playing either the same thing at the same time, or maybe they're playing the same frequency, so the same pitch, anything like that. Okay, but the same exact thing happens in light. Let's say we have the sun up there, right? The sun's coming through, but now let's say we have a little cardboard box with a slit in the top. You'd expect, right, the sun to go through the slit, and if we have a piece of paper on the bottom, the sun's just going to make one little line of sunlight on that piece of paper. Right? That's kind of what we'd expect, because the sun in other places just hits the box and stops, so it doesn't get in. This is not what happens. which is really strange. What actually happens is we get this box, and if we zoom in, when the sunlight comes and hits, we actually get sunlight that hits this corner of the box and this corner of the box. And it just so happens that those become sources of light themselves. That's just how they act. So they act like we get one source of light right there that just creates these wave fronts. Get this one source of light that creates these wave fronts. And then you get the other source of light that creates the wave fronts in exactly the same kind of way. So the other part of the box that creates these wave fronts in exactly the same kind of way. So right, we get all these maxima, right? Maxima. Wow, I'm really bad at straight lines. Um, if we were to draw just more waves, you would see there should be some pretty straight lines. If I was better at drawing, and if many things in life would be easier if I was better at drawing, I've decided. Um, so then another one right here. Okay, that's going to be a little bit better. All right, so yes, we get this constructive interference right there. We get constructive interference over there. We get constructive interference right there. Again, all these places where we would get this constructive interference where the waves are adding together, right? The E field vectors are adding up together. But then we get all these spots, right, of the destructive interference where one's at its peak and the other's at its trough. So one's got amplitude of A, one with negative A. And those will, right, add to be zero. One's at its peak, the other's at its trough. Peak and trough, peak and trough, peak and trough. So we get all these lines of, now this is our destructive interference. So anywhere, just pretend I'm a little bit better at drawing. So those would be straight lines in reality. So we get constructive interference and destructive interference. So what happens is if we put a piece of paper here, what we see, right, this is constructive interference. We see a really bright spot in the middle. We see a really bright spot in the middle. And then at the minimum, right, the minima, we see the spot where there's no light. And then we move over to the side a little bit, and then you see right over here, there's going to be another maximum. So this maxima here where there's light, move over to each side, there's another maxima. So that looks like this, right? Where that's another maximum, that's another bright spot. But then if you follow these waves out to the side, right, this tracks down another minimum, tracks down another minimum. And then if you follow it over, this tracks down for another maximum, This one, if I was better at drawing, track down right there for another maximum. So we get all these minima and maxima just all in a row where you have either zero light or you have this constructive interference to give you double the light, which is just really, really awesome. So these diffraction patterns, this is, by the way, this is called single slit diffraction. Single slit diffraction. Single slit, we have one slit, and then diffraction is just anything where you get multiple sources of light that interfere with each other, and you have this kind of alternating constructive versus destructive interference. So if we were to look up single slit diffraction and then just head on over to images, you see these really cool things. I mean, there's people talking about the same phenomenon here, but this is really what I'm talking about. You get this center. I'm just going to copy this image and bring it over here. That's a beautiful picture. Maybe we can make this picture small enough to actually be worth our while to see. Potentially. Bear with me. Okay. So right, if we look at all this diffraction stuff here, you get that maximum that's right in the middle, and then you get this minimum here. Then you get, or another maximum, and then a minimum, and then a maximum. So right everywhere, right there, all these minima where there's just no light. And then the further we get away from the center, right, because this is directly incident light right here, because that's coming straight down from the sun, right along this ray here. So that's coming straight down. So you get this really bright spot in the middle. But as you get further and further away, the light has to take on more of this curve and more of the curve. And the more light has to curve, the dimmer it'll be. Okay, so that's pretty much single slit diffraction. The other thing, though, that we can do from this is we can calculate a little bit of, we can calculate some of these things. I'm just now going to turn this all sideways and say that we have the single slit diffraction here. So, right, this is our result. That's our result. If we have a slit that is some width d, let's say that we have just some length L from the screen to the slit. What we call this, we call this is our first order minimum. We call this is our second order minimum. We use that to represent, we use M to represent our order. So then this is M, and it's just you count away from the central maximum. Because you might be able to see on this is twice as wide. The central maximum is twice as wide as any of the other maxima. So from here to there, we call that 1. And then every minimum out from that, we count it as M. We count it as M. What we actually see from this is if we were to take two waves, if we take two waves here and go from this to be right there, and then the other wave from the other side, let's use brown, I guess, to be from the other side, right? A minimum is when they are, a half wavelength apart, right? One's at its peak and one's at its trough, so they're a half wavelength apart. The geometry that ends up coming out of this, and I could talk you through the geometry if you're interested, but I'm not going to spend the time to do that. Because it's half a wavelength, you can get the distance of the slit times the sine of theta, and theta ends up being whatever it is from the center here to the minimum, and that is the angle that it makes with the central maximum. The angle that it makes with the central maximum, that is theta. So, right, if we were to go the other way, if we were to go to, I cannot draw a straight line. If we were to go to the second order one, right, get theta, that's for the second order, theta for the first order. That theta would be bigger by about twice as much. But this is the equation that they end up spitting out at you, and that's what's on the equation sheet. This is not useful, though, because sine of theta, we don't know what theta is. It's almost impossible to measure because it is so freaking small. But what we can use is the small sine approximation, or the small angle approximation. The small angle approximation tells us that theta is approximately equal to the sine of theta is approximately equal to the tangent of theta. Tangent of theta is much more useful, though, because we can measure from the central maximum, we can measure from that to the minimum, and we're just going to call that distance y. All right, so we have some distance y between the central maximum and our minimum, and that would be the same distance for all of our minima. So from one minima to the next minima, that is a distance y. Tangent of theta, right, we can say is approximately equal to sine theta, but tangent of theta, we can just take that as being equal to whatever our distance y is, and we'll use this one right here to say it's first order, y over L, right? It's this leg right here over the length there. So that's the length right between the slit and the screen. So that's our slit, and our slit is some distance d. So that's our tangent of theta. So we can plug that in for sine theta. So what we actually get out of this is dy over L equals m lambda. And this y is just the distance from the central maximum to whatever m order minimum you are measuring. So what this does is this is the useful equation. We can actually measure the distance of a slit by just saying, okay, we have some screen that's some distance L away. We can measure y, and that's the distance between the central maximum and whatever minimum that we have, and then m lambda. So if we know what wavelength of light is getting produced, then we can plug that in and find the distance of the slit. Or we could, if we know the distance of the slit, we can find what the wavelength of light is by measuring all these quantities. Okay, so it's called single slit diffraction. What's really important is that AP does not give you this. AP just does not give you this. What AP does give you, and I don't remember if I have this pulled up right now. I do not. What AP does give you is they just give you that first equation, but they expect you to use the second equation. They give you this d sine theta equals m lambda. They give you this right here, and they just expect you to have the other one basically memorized. They also tell you that the change in wavelength is m lambda, or the delta L, so the change in distance is m lambda. So they tell you all that, but this is the equation they give you. This is the equation that they expect you to use. So you have to be able to go from d sine theta to dy over L equals m lambda. You have to be able to make that conversion on your own and to show where that comes from, because AP will expect you to use it, but they don't give it to you. All right, I've rambled on for enough time now. It's been a little over 40 minutes. We will do stuff with this in class. We're going to use this, hopefully, I hope, to measure. If we have enough time, we can use this to measure the width of a human hair. If we know what wavelength it is, we can measure y. We can put a screen a certain distance away, and then we just measure to all the different orders. The order is m, right? If we just measure to all the different orders, then we can just plug all this in and say, okay, that's our distance there. And that would give us the width of a human hair. If you have any questions, as always, let me know. But otherwise, I'm going to stop this video, and I'll see you next time in class.